Periodic table reactivity and general family trends. Let's first start off with the chemical reactivity for metals. The most reactive metal is francium, or cesium if you want to look at it that way. Francium is a very rare metal. It is a result of radioactivity. At any one time, there's probably only 100 atoms in the world. So again, it's a product of nuclear decay. So when we look at francium, francium is a very, very large atom, and it's because it's on the 7th energy level with a 7s1 electron. It also experiences shielding effect because it's a large atom. Again, shielding effect is when the core electrons shield the nuclear pull for the valence electrons. Metals, they react by losing electrons, and so because that valence electron is very, very loosely held, it's easy to pull that electron off. This makes francium extremely reactive, and we see the trend on the periodic table is as you go down a family, so as you go down the alkali metals, you are adding on energy levels or shells, and so the atom keeps getting larger and larger, and they all have one valence electron, and as you go down the family, the atom gets bigger, and it's easier and easier to remove that one valence electron. And we find that the trend goes as you go to francium, it becomes more reactive. So your alkaline earth metals, they tend to be very, very reactive. And then we have our transition metals. It's not a fail-safe trend. There are exceptions all over the place, but in general, as you go towards francium, it becomes more reactive. When we look at non-metals, the most reactive non-metal is fluorine. Non-metals, they tend to gain electrons, and fluorine is a very, very small atom. And because it's small, its nucleus is able to reach out and pull in an electron and drag it in. And this makes it very, very reactive. As you go down the halogen family, you find that the atoms get larger and larger. And so by the time you get to, let's say, iodine, it is not as reactive. And that's because it's a larger atom, so it has shielding effect. The nucleus has a hard time reaching through the core electrons to pull in additional electrons. So we find that fluorine is a very, very reactive element. Chlorine is also very, very reactive. Both of these gases are highly poisonous. And then we have bromine, which is a liquid, and it's not as reactive, and then iodine is not as reactive because of its size, as I mentioned before. So as we go across the periodic table towards fluorine, and this is for nonmetals, and as I go towards fluorine, it's going to get more and more reactive. And you should know that your noble gases, they are non-reactive. So metallic and non-metallic properties and metalloids. So you should know that this little stair-step dividing line, we have metals on this side and non-metals on this other side, and the metalloids are in between. There's only 6 of them. So you should be familiar with those. But as we go towards francium, it does increase in metallic character. And please remember that hydrogen, even though it's over here with the metals, it is a non-metal. When you are looking at the periodic table and looking at trends, you need to remember a trend is an observation, not an explanation. So if you're asked to compare 2 atoms, you cannot just list the trend. You need to tell why. So when the AP board or myself, when you are given 2 elements on the periodic table, describe both of them in your answer. You want to try to work in Coulomb's law. Usually you're asked to do that. And you should look to see what is the same about those 2 atoms and what is different. And as you describe what is the same and what is different, you should be able to explain the trend. So let's look at an example. So explain why fluorine has a higher ionization energy than oxygen. So I need to figure out what's the same and what is different. So on the periodic table, I see that fluorine and oxygen are right next to each other on the periodic table. So I know that their valence electrons are in the same energy level. I know that oxygen has 8 protons and fluorine has 9 protons. So being on the same energy level, I know that fluorine will have a higher nuclear charge. This will cause the electron cloud to get pulled in a little bit tighter for fluorine. So fluorine is a smaller atom. So when you look at the higher ionization energy, so I know that fluorine is higher, but why? Why is it higher? Well, it's because it's a smaller atom and it has a higher nuclear charge than oxygen does. So this is the thought process that you want to go through. I didn't bring in Coulomb's law, but I could. So I could say Coulomb's law says that the closer two opposite charges are, then the more attraction force that is there. And so I can say because the protons of fluorine and the electrons of fluorine are closer together than oxygens, it's a smaller atom, and therefore it will take more energy to take away those valence electrons. Here's an example of some other trends that we have talked about, and I'm just going to talk through them. These are very AP style like questions. So let's talk first about PES peaks. So why is the 1s orbital harder to remove from fluorine than it is for oxygen? So this refers to that last slide that we just talked about. Fluorine is a smaller atom than oxygen. It has a greater nuclear charge with 9 protons versus oxygen's 8 protons. Therefore, the atom is smaller. It's going to be harder to remove the 1s peak from fluorine than oxygen because it's closer to the nucleus. And that goes along with Coulomb's law. Atom and ion size. So why is Kr smaller than Br minus? So looking at similarities and differences, we find that they have the same number of electrons, but bromine has 1 less proton than krypton does. I can also talk about how an anion is always larger than its atom. So we have bromine atom is going to be a little bit bigger than krypton, and then if you add 1 electron to bromine for a bromide ion, it's going to be even larger. So I can talk about that. And you can add Coulomb's law with the sizes and how krypton has a higher nuclear charge than the bromide ion. It's going to be even smaller. Ionization energy. Why is the valence electron in lithium harder to remove than sodium? So I talk about the sizes of the atoms. I can talk about how they both have 1 valence electron. Sodium being larger, it's going to be easier to remove that outer electron. Electron affinity. Why does fluorine have a greater magnitude electron affinity than oxygen? And I can talk about how it's a smaller atom and it's going to have a very attractive nucleus because it has a higher nuclear charge than does oxygen, and so its electron affinity is going to be greater. Reactivity. Why is bromine more reactive than iodine? So I can talk about how iodine is a larger atom than bromine. Nonmetals want to gain electrons. Iodine has shielding effect that prevents that nucleus from reaching out and grabbing another electron, and so it's just a little less reactive than bromine. With bromine being a smaller atom, it's easier for its nucleus to reach out and grab an additional electron. A great periodic table to ever use in this class is ptable.com, and you can look up trends and click on each of the elements to get more information about them. You should know general characteristics of metals and of nonmetals, and of course metalloids would be in between. So metalloids might be shiny like a metal but brittle like a nonmetal. But go ahead and pause the video and you can take a look at each of these trends for the metals and nonmetals. For metals, some little definitions. Ductile means being able to pull out into a wire. Lustrous means it's shiny. Malleable means that you can take a hammer to a metal and you can pound it into a shape, or you can mold it into a shape. But those are general trends of metals and of nonmetals. Hydrogen does not have a family, even though it's stuck over the alkali metals. It is not an alkali metal, and we're going to see throughout the year these trends that hydrogen can do. So hydrogen can lose its electron. When it does this, all that's left is just a proton, which is very, very highly reactive. And it also can share an electron, and it can take an electron. The main group metals, the alkali metals, they have an oxidation number of +1 always. The alkaline earth metals have an oxidation number of +2 always. They are your S electron metals. They're very reactive. They're our most reactive metals. There are also some metals in the corner of your periodic table. I call them the P metals, so down here. So they're below that dividing line between metals and nonmetals. And they are known as the poisoner's corner here because most of them are poisonous to humans. And they're a little bit unique. They have P electrons. There will be some links on the Canvas course where you can see some reactions of alkali metals in water. The transition metals, they have very many different oxidation states, and the reason for their hardness is because of the d electrons. So these metals are much harder than your alkali metals and your alkaline earth metals. We use these metals in construction and also in wiring and in coins and jewelry. When you take a metal and melt it together, you make what's called an alloy, which we will talk about when we talk about metallic bonding later on in the year. An alloy, typically when you melt two metals together, you get characteristics of each metal. So it usually makes your metal better. So in other words, you can make it stronger. Your lanthanides, these are rare earth metals. They're your 4F row. We use this a lot in wiring. So in our cell phones, we have wires that come from the rare earth metals. And then the last row on the bottom of your periodic table are your actinides. These are all unstable. They're radioactive. In history, they have added this to the glazes of pottery, and it makes a very brilliant orange color. But unfortunately, it is very radioactive. But there is a high desire for this type of pottery. There are actually collectors out there. Also in the 1800s, they added uranium to glass, and it made it glow in the dark. And that is also highly collectible, but probably don't want to store it in the main living areas of your house. In our smoke detectors, they do use americium, which is an actinide. It's an alpha emitter, and it helps detect if there's smoke in a home.